right, a ratio is typically the comparison of two values by division. And if we have two ratios that are actually equal to each other, then it is a proportion. So note we have these two triangles over here, and notice how their angles are all marked as congruent, and that will become really important to us in the near future. But anyways, these two, we're told to first write a ratio comparing the lengths of MN, NO, and OM. Well, MN right there has a length of 5, so I'm going to write that first. So it's 5 to the length of NO, which is 7, to the length of OM, which is 3. And so that order is important, 5 to 7 to 3. And we can write ratios in several ways. We could also do it like this, 5 to 7 to 3. That's still how we read it. It says write a ratio comparing MN to PQ in 3 ways. Well, MN to PQ, the length of MN is 5 to the length of PQ, which is 10. 5 to 10, well, we could write it like that with the word 2. We could write it with the colon like we did up here, or we could write it, because what is a ratio? It's really using that division. We could write this as 5 to 10. So there are 3 ways. Finally, write a proportion that shows that MN to PQ, we've already written that, that's 5 over 10, is going to be equal to NO to QR. NO is 7 over QR, which is 14. Well, notice how both of these reduce to be a half. The value in the numerator is half of the value in the denominator. So yes, this is a true statement. This is a proportion, because we can set those two ratios equal, and it is a true statement. Now, we can solve proportions in many ways. Probably the easiest way would be to use a cross product. And also, when we're thinking about a proportion, the extremes are the smallest and the largest number. Typically, that would be the top number on the left, the largest number on the right. So the top number on the left, the bottom number on the right are typically the extremes. 3 would be the smallest number in this proportion, while 50 would be the largest. But what we can do is we can solve the proportion by multiplying together the extremes, multiplying together the means, the two values that are kind of not so large. 3 times 50 is 150, so we multiply the extremes. We set that equal to the product of the means. So 150 equals 15x, divide by 15, and of course x would come out to be 10. If two figures have the same shape, but not necessarily the same size, they are considered similar. In the diagram, these two triangles would be similar to each other. All congruent figures, they say, are similar, but not all similar figures are congruent. So think about that. Every congruent figure naturally has the same shape, but not all similar figures will have the same size. They're different sizes of the same thing. It's kind of like a model car and the actual car. They're similar. We can learn a lot about the large car by looking at the model car, but they're not congruent. They're not exactly the same size. And so it says here, in similar polygons, the corresponding angles are congruent, and the corresponding sides are proportional. So, remember I was kind of referencing this earlier, all the angles of this triangle are congruent to all the angles of this one down here, so that would mean they are similar, because in similar shapes, their angles are exactly the same, and their sides will always be proportional. If all the angles are the same measurement, the sides are going to be proportional. And so here we can see they have congruent angles, and each pair of corresponding sides has the same relationship. Notice we can check that. 3 to 6 is equal to 2 to 4, which is equal to 5 to 10. they're not congruent, they're not exactly the same, but notice how it's always double that 3 to get 6, double the 2, double the 5. It's the same ratio that we're setting up. It's always twice as big in the larger triangle. And notice they check that here, they put the larger over the smaller down here, and so they got that same relationship, twice as big in the larger than the smaller. Here it says find the unknown side lengths in the two similar triangles. We know they're similar because they have the same angle measures. All their angles are congruent. So that means we can solve for these missing pieces by setting up some proportions. Notice the piece they gave us is that 4 became 16. What happened from 4 to get 16? We were multiplying times 4. Well, we can do that exact same thing. 7 times 4 means it's going to be 28 for this side. 5 times 4 means it's going to be 20 for that side right there. If you want to see this with a proportion, we could. 4 to 16, well, you want to keep that ratio. 5 becomes A. 4 to 16 as 5 is to A. We can multiply the extremes, multiply the means. 5 times 16 is 80, equals 4 times A. Divide both sides by 4, and we know 80 divided by 4 gives us 20, just as expected right there. A similarity statement is a statement indicating that two polygons are similar by listing their vertices in order of their correspondence. Just like a congruent statement was for triangles, the order was very important. This is a similarity statement. This is saying that those triangles are, or those polygons are similar. And so we do want to be careful with our order. The order matters because the letters are corresponding to vertices, and so we would be able to match up what vertices have the same angle measure by just looking at the names. So take a look here. We have two polygons, and that is our symbol for similarity. It might be hard to see there. It is basically a squiggly. Kind of like for congruence, we have an equals with that on top. Similarity is just that symbol that's kind of on top of our congruent symbol. So they're not equal, but they are the same shape. So here it says, what are the measures of angle T and angle Z? Well, let's do a little poking around here. If this is 110, X is 110. Well, X corresponds to T. So if X is 110, T has to be 110 degrees because those are both the second letter in the similarity statement. If V is 125 degrees, well, V corresponds to Z, so Z must be 125 degrees. So angle T is 110 degrees, while angle Z is 125. They didn't give us a lot of information, but understanding our similarity statement, we're able to answer this because we know the polygons that are similar have congruent angles. It's their sides that are changing. Their angles be the same. What is the length of YZ? So I'm going to clear out this angle stuff. I want to find the length of YZ. Well, YZ corresponds to UV. So looking over here, UV I know has a length of 4. So if I let YZ be, well, I'll just let it be YZ. 4 is to YZ, but we need something to compare this to. We need two sides that we know, since these are similar, we know kind of what that proportion was, that ratio we're working off of. And we have SV is 6, and so that will be proportional to WZ. 6 is to 15. And notice how I kept this order important. The smaller polygon to the larger, 4 to Y over Z, is equal to the smaller to the larger. 6 went with 15. So I set that up. And those aren't just two random sides, but they are sides that are corresponding. I can use my cross products. 15 times 4 is 60. YZ times 6. 6YZ. Divide both sides by 6. And of course, YZ would come out to be 10. Finally, this girl is using a mirror and similar triangles to determine the height of a small tree. She places the mirror at the distance where she can see the top of the tree in the mirror. According to the measures of the triangles, what is the height of the tree to the nearest inch? Okay, so these are similar triangles. That's what we were told repeatedly. And I can see the base is going to match up to the base, the smaller 36 to the larger 52. If she is 66 inches, well, that's going to match to the height of x. Notice how those are the corresponding sides. Smaller to larger equals smaller to larger. A little bit larger numbers to work with too. So pull out the calculator. 36 times x. 66 times 42. Divide both sides by 36. And x comes out to be 77. Since we're working with inches, that tree would have to be 77 inches tall.